Hey everybody, as promised, here are some of the recorded lectures we were going to do. And the first thing I want to talk to you about with this is this idea of pKa. Now, I kind of gave this short shrift because I thought we were running out of time, and I hold to my original idea. Hold on one sec, I need to change this background because it's going to bug me. There we go. pKa. Now, if you'll remember, there were 5 main ways of predicting the pKa of an organic molecule. One was the size of that counterion, where the bigger X means lower the pKa. And remember, pKa is a log scale. So the lower the pKa, negatives included, the more acidic it is. The second one was electronegativity of X. And the rule here was the higher the electronegativity of whatever that conjugate base group is, the lower the pKa. Now the other three I kind of left nebulous and said, go learn these yourselves, which I've been doing this long enough to know that go learn this yourself means forget all about it and then complain I put it on the test. So let's go through some of them here. The next ones we're going to talk about are hybridization. Honestly, of these next three, D-I-Z-A-T-I-O-N. Of these three, this is probably the most important synthetically. Next is resonance. And finally, induction. Now, if there's one of these we don't get to, and it's induction, I'm not going to cry. Because, frankly, that's the least important of this set. So we've covered these two. Let's go ahead and talk about the easy one, which is hybridization. Now, as a quick reminder, we're talking about this reaction here. Darn it. All right. And the part of this that's really important is here. The more stable that X group is, the more likely this is to be acidic and give up that proton. All right, so here is the rule. As you increase S character in your carbon, because the hybridization as a method of predicting pKa only applies in carbon-based, on carbon atoms. As you increase the S character in your carbon, you're going to lower the pKa. More acidic it is. So let's list these out. sp3, sp2, and sp. They look like this. What else is bonded on those groups? I'm glad you asked. It doesn't matter. All we're really interested in is the carbon with the hydrogens. All right, so here are the hybridizations, sp3, sp2, sp. There are examples of each. Now, let's really quick do some fun math and do percent S character. Percent S character. For sp3, it is 25% S character. For sp2, it's 33%. And for sp, it is 50%. Here are the pKa's. The hybridization of an sp3 hybridized carbon is 50. This is one of those numbers that I'm not going to tell you to memorize, but shouldn't be that hard to keep in your head. All right? It's a pKa of 50. Hybridization of an sp2 hybridized carbon is 45. That's not very much at all. 5 to the 10 to the 5th times jump. But down here, the sp hybridized atom Oh, darn it. Don't you hate it when you mess things up? I know I do. The pKa is 25. Folks, I'll be very honest with you. Of this entire argument and method of determining the hybridizations, this is the only one that is synthetically useful. So I would, I don't like to memorize things, but I think this one would be really handy for you. You should keep in mind that the hybridization of an sp hybridized atom is hybridization 25%. The pKa of an sp hybridized carbon atom is 25. That is synthetically useful. We'll get back to it as we go on through the course. So that's hybridization. Let's go ahead now and talk about resonance really quickly. I like to call resonance a game of atomic, or I suppose technically, ionic, hot potato. Here's some examples of it. This is ethanol and has the pKa of about 16. Here's acetic acid, which is really just vinegar with an attitude problem. The pKa of acetic acid is 4.75. That is a huge jump. Now, you're probably already saying, well, it's the double-bonded carbon. And I got to say, you're right. It is the double-bonded carbon, but maybe not exactly the way you think. All right? So, how is this a game of atomic hot potato? I want you to think about it this way. Charges are hot. They're high energy. And therefore, low stability. And if there's anything a molecule hates, it's not being stable. So, something like ethanol here. When you deprotonate it, ethanol here has what we call a localized charge, meaning that negative bond is stuck in one place and isn't going that negative charge is stuck in one place and isn't going anywhere. All right? Now, let's do the same thing, but we're going to do it with acetic acid. So why, dear God, why is that so stable and the other one isn't? The key here is resonance. Delocalization of a charge over multiple atoms to decrease overall energy. And when your energy decreases, your stability of the negative charge increases, which means the pKa of this lowers. All right, how does this work? Well, on a slightly graphic scale, here's what we see. This negative charge distributes itself into that carbon, or rather above that carbon-carbon bond. In so doing, that puts too many electron pairs around this carbon right there. that puts 5 electron pairs, it can only have 4. So something has got to break. Your options are carbon-carbon sigma, carbon-oxygen sigma, or carbon-oxygen sigma, or carbon-oxygen pi bond. And what is the weakest bond to break? Always is going to be a pi bond. So we represent it like this. Now, this is a good way of keeping up with your directionality of your arrows. These are 2-headed arrows. 2 electrons are moving to do these, and you'll notice they're going in the direction of electron flow. So what we get on the other side of this is an equilibrium event, is this. Now, if you're looking at that and you're saying, wow, that looks exactly the same, like we just rotated along an axis, you're not entirely wrong. The 2 resonance forms are very, very similar. All right, so with these are both called resonance contributors. You can also draw a resonance hybrid, just not like that. You can also draw a resonance hybrid, where you draw in the sigma bonded skeleton and you put dashed lines everywhere there was pi bond density and a partial charge wherever a full charge showed up. So what this is telling you is that the negative charge from that deprotonation of your conjugate base is spread over both of those oxygen atoms. I rush to point out that at no time does this carbon bear any kind of charge. This is all done through negative charges and pi bonds. Pi bonds are crucial to resonance. All right, ladies and gentlemen, that's all for this video. I hope you enjoyed it. Like and subscribe. And I will, next time we talk, which will probably be in a few minutes for me, is going to be continuing this idea of SN2 reactions. All right, have a great day.